In this video, we are going to learn about regularization. Regularization is an important technique to improve the accuracy of a classification or a regression problem. In fact, regularization is an important hyperparameter tuning exercise. Okay, so before getting into regularization, let's understand overfitting and underfitting, or let's summarize overfitting and underfitting. This is something that we have seen earlier too, right? Overfitting is, we are overdoing the fitment. In underfitting, there is no fitment at all, right? A statistical model is unable to capture the trend of the data in underfitting, right? Whereas in overfitting, the model works well, for in training consideration. When I give a new data set, right, or even test data for that matter, the model doesn't do a good job, the fit is not good. That is when overfitting results. Okay, this is due to high variance and low bias, right? And this is due to high bias and low variance. Okay, these two are entirely different things. In underfitting, the most important thing is the model is too simple. That is one. Fewer data points, right? Data set is not sufficient, and the data is not cleansed. Okay, possibly contains noise in it, right? This is the reason you have underfitting. Whereas when it comes to overfitting, the model is too complex, right? There are far too many parameters here, far too many variables here, right? Here the data may be too huge, right? You allow the model to overlearn, right? This is like a student preparing well for the examination, prepares so well, does well during all the term tests, but does poorly, in the final examination. That is the overfit. In underfit, the student doesn't understand anything. Please note that, right? The student does not grasp the subject. That is underfitting. In overfitting, okay, there is over preparation, right? To the extent that some of the key aspects of the examination or the subject are missed, right? That is overfitting. Now, regularization is one of the finest techniques to address overfitting, right? Underfitting, how will you address? You clean the data, right? You bring more data points. All the models that are done for the purpose of explaining or academic purposes, right, typically will have underfitting issue, right, because the number of data points are few, right? It is not a real data set. Okay, or you have not done the cleansing properly. Whereas in overfitting, I have more number of parameters, right? The complexity is more. Okay, so I will address the problem of overfitting through a process known as regularization. Okay, regularization is used to avoid overfitting of the data. So how do I go about doing regularization? I add a penalty term, to the best fit. Okay, what does regularization actually does? It keeps any one parameter, right, or any one variable from growing boundlessly. You don't want one or two variables, to have an undue influence on the data set, right? Only when you have, such scenario that you have overfitting, right? So regularization is performed to keep those parameters or variables under check, right? So regularization is an important technique to address the problem of overfitting, which is a real problem, in the real world. Okay. So there are two types of regularization techniques, that you need to be aware of. One is known as ridge regression and the other is known as lasso regression. Okay. So what is this ridge and what is this lasso? Okay. ridge and lasso, in both the scenarios, I'm adding a penalty term. Okay. I add penalty to the best fit so that, these issues are addressed. Okay. In both the penalties are added, but the way in which I add is different. If you recollect, the mean sum of square, right? MSE is what? Mean sum of square of the error term. Okay. This is a square term, right? My MSE is what? Predicted minus actual, the whole square, right? In lasso, okay, and in ridge, I add this term, okay. Rather, this expression is added. What is M? M is nothing but slope, right? When I say Mi, different instances of slope. Okay. In this case, the absolute value of slope is taken. In this case, the square of the slope is taken, and then it is multiplied by lambda, which is nothing but my regularization parameter. Right? This is what happens in the case of lasso and ridge. The formula is the same. Okay. Mean squared error, and I add this term. Okay. To adjust for the overfitting that is happening in my data set. Okay. Now, let's understand this lasso and ridge a bit more. Okay. So, what is the difference between lasso and ridge? Okay. So, this is also, as I said, regularization parameter is also known as the penalty, right? Because this whole thing is the penalty that is added, penalty term, right? Or the penalty parameter, regularization parameter or the penalty parameter. Okay. In fact, this lambda is also known as a hyperparameter. Okay. We tune or we find the best value for lambda, okay, through a iterative process, right? We start with 0, 0.1, 0.2, and so on and so forth. Okay. Hyperparameter tuning. We use a process known as grid search CV. Okay. In fact, this is a library that is part of scalar. Okay. CV stands for cross validation. Okay. In fact, this is a hyperparameter, and this is known as hyperparameter tuning. So what we are doing is the tuning of this hyperparameter so that the overfitting issue is addressed. Okay. How do you do the tuning process? It is an iterative process. You give different values of lambda, and you check, how the fit changes, right? How much the overfitted issue is addressed, right? We do all of this programmatically. Okay. So this is lasso and ridge, two different ways in which I do regularization. As I said, regularization is a hyperparameter. So what we are actually doing is hyperparameter tuning. Okay, these are all terminologies that you need to be aware of, right? So you're tuning, right? It is just like you tune the frequency, in a radio, right? You are tuning the frequency in the radio to the correct radio station, to the radio station you are looking for, right? So the same thing we are doing here. Okay? It is the same thing that we are doing, in this particular case also. Okay, so let's understand this lasso and ridge a bit more in detail. Lasso is known as the L1 regularization technique, whereas this is known as an L2 regularization technique. It contains absolute weights. Lasso, this contains weighted square, right? We saw that here, right? This is what modulus, which is nothing but absolute, right? This is a modulus term, whereas this is a square term. Okay, and that's what I am referring here, absolute. Here, lasso, what it does is it shrinks some of the coefficients to 0. Okay, it shrinks. When I say shrinking the coefficient, you have like m1 x1, m2 x2, m3 x3, right? So on and so forth. It shrinks some of the coefficients, to 0. Because it shrinks, what will happen if the coefficient becomes 0? This whole term will go away, right? So you are left with, let's say, m4 x4, m5 x5, so on and so forth. So x1 and x2 goes away and you are left with x3, x4, x5, so on and so forth, right? So because it reduces some of the coefficients to 0, it is also known as variable selection or a feature selection technique. What is feature selection? I select some of the features that are relevant for the model, right? If I remove some of the parameters, my fit is better, overfitting issue is addressed. Okay. Whereas in the case of L2, it shrinks the coefficient but eliminates none. Okay. L2, it actually addresses the problem of multicollinearity. Okay. In ridge, it penalizes one big weight more than many small weights. Okay. As I said, it doesn't allow any one factor to have undue influence on the output. Okay. Here, it brings you to 0, whereas here it is about minimizing. Okay. It minimizes the coefficient. So ridge tends to excel in cases where there is a grouping of regressors, which is nothing but a group of variables, independent variables, that move in tandem during successive optimization steps. This is nothing but multicollinearity. Okay. Ridge introduces bias in order to reduce variance. Whereas Lasso, it eliminates some of the variables from the model altogether. So for overfitting, Lasso is the best technique. Rather, is better of the two. If there is multicollinearity, in the data set, L2 is better. Okay. The other thing, it doesn't get affected by outliers, whereas L2 gets affected by outliers significantly. Right? So you can say that L1 is good in some ways, L2 is good in some ways, right? If my problem is overfitting alone, okay, I have to go for L1. If my problem is a multicollinearity problem, I go for L2, right? The VIF that I described, variance, that is one of the ways to address multicollinearity. L2 is another way to address multicollinearity. As I indicated, this is a hyperparameter which I tune. Okay. Now, if someone says, I want the best of both worlds, this is known as elastic net. Okay. This is part of a deep learning solution. Okay. What we saw today is a case of hyperparameter tuning. The penalty or lambda is actually a hyperparameter, and we tuned the regression classification model for the optimal value of lambda, right? That's what we did. What are the other types of hyperparameters that are tuned in machine learning or deep learning scenario? The learning rate, that is a hyperparameter. The sigma and c value, in support vector machine. The k value and k nearest neighbor. All these are hyperparameters. Please note that these are actually outside your, the test versus training process, right? So we go and find out the optimal value of these hyperparameters so that the accuracy or the issues in the model are addressed. Either the accuracy is enhanced or the issues are addressed, right? So this, how do we go about the process of tuning? We use grid search CV or randomized search CV. Okay. So in grid search CV, different values of lambda, in regularization, we feed in different values of lambda. Okay. And then we find the optimal value of the hyperparameter. That's what happens in a tuning process. Okay,